Hello and welcome to the session. I am Dr. Akshay Kumar from School of Computer and Information Sciences, and today I will be discussing with you about graph representation and traversal. In order to define graph representation and traversal, let us first define the term called graph itself. So, a graph is a data structure which is defined as G, which consists of two things, V and E. Okay, so G basically defined as a term consisting of V as well as E. Now these two things, okay, so it comprises of two sets of object. So one set of object is V, another set of object is E. All right, and the set of object which we call V is set of vertices. So a graph can have n number of vertices, large number of vertices, and we are showing here V1, V2 and so on, right. And there is a set of edges. So E is representing the set of edges with E1, E2 and so on. Okay. So if we look here, now these are okay, everything A, B, C, D, E, F, these are the vertices and these are the edges, all right. So these are all the edges of these vertices. So what is the property? Vertex is basically represented with a circle and an edge is is basically connecting two vertices, okay. So if we see this particular graph, it consists of the set of vertices is A up to F, right. So A, B, C, D, E and F. So this is set of vertices and the set of edges are, one is AB, that is over here, then there is AC which is being represented, then BE, so from B to E, okay, B to D, B to C, right. So BC, B to D, B to C, right. Then we have edges from C to D, C to F, C to B is already there, that BC is already there, therefore, it is going to be C to D and C to F, these two edges are going to be there. Then from D, we are having edges to F, all right. So, there is an edge to F and there is an edge to E from the D. So, these are the set of edges, okay. So, vertices are basically unordered set of nodes, all right. So, their ordering does not matter and an edge is identified with an unordered pair of vertices. So, edge is basically a set of unordered set of vertices like C, D. So, C, D is basically a set which, since this particular edge is in both, I mean there is no particular direction in for this particular edge. So, it is same as DC. So, this is basically unordered pair, okay, an unordered set of basically that is a pair of vertices is representing edge, where Vi and Vj are the n vertices of the edge Ek. So, this is how we define a graph, and graph is represented like this, okay. So, it pictorially it is represented, okay, that is what is being shown here. Now, why we are doing, or what is the importance of graph? In fact, graphs are the most widely used mathematical structures, okay, and it can be used to model many different problems, okay. Social networks that comprise million of user or interest groups are represented as nodes, and interdependencies among nodes through mutual interest and common friends are represented as edges. Okay. Many social networks use graph-based algorithms like Facebook friend request suggestion algorithm. So that is a graph-based algorithm. Similarly, Google's PageRank algorithm is also a graph-based algorithm. And many applications like airline scheduling, computer networks, the road networks, they are also modeled using graphs. Now, some popular graph-based algorithms which we might be discussing in this particular course is to find the minimum cost spanning tree. We will be discussing this. Then shortest path algorithm between every pair of vertices. So, and maximum bipartite matching. So, all these three we will be discussing in the subsequent sessions. Okay. Now, what are the different types of graphs? Well, we will not elaborate on it, but just very basic type of graphs would like to see. So, the very first type of graph is a simple graph. So, a graph contains vertices and edges with many variations in them, right? Most of the variations are due to the edges, such as directed edges, undirected edges, and the number of edges. So, these basically may determine the type of graphs. So, a simple graph is the one in which each edge is connected with two different vertices. So, if this particular edge, okay, so 1, 2, 3, right? So, this edge is between nodes 1 and 3, all right, whereas this node is between 1 and 6, okay. So, there is no self loop. If there is a loop of this kind, that is a self loop, it is not allowed. And no parallel edges. Parallel edges may be in the form there is an edge from 1 to 2, there is another edge, that is also not allowed. Otherwise, the graph is not going to be simple anymore. All right. So, these are the properties. So, this is typically a simple graph. This kind of edge is not allowed. The second edge, already one edge is there. The second edge or the parallel edge is not allowed, and the self edge to a particular node is also not allowed in a simple graph. The other type of graph types basically, that is called multi-graph, a simple graph with multiple edges. So, now we are allowing two edges between A and E, all right. So, if we are allowing two edges, then it is called a multi-graph, all right. The weight, if we assign weight to these edges, then they might be different, okay. This is something like if we have a road network, okay, and there are two paths between a particular source and a destination, all right. Maybe for example, from Delhi to Mumbai. So, there may be two different paths and both will be having different length. So, that can be modeled with the help of a multi-graph. Then comes the undirected graphs. The edges do not have any direction and all the edges are bidirectional in this particular case. So, basically A to B or B to A, both are the same edge. So, we can traverse in both the direction from A to B as well as from B to A using this particular edge, all right. There is something called directed graph. So, in such graphs, the edges have a direction. It is also called a digraph. So, direction is usually indicated with an arrow on the edge. So, you can see there is an arrow here which is indicating the direction that this edge is from A to F and not from F to A, right. So, it is unidirectional or one directional only. So, that is why it is called a directed graph. So, is this particular node, if each of these edge is having a direction, and that is why, okay. So, now this is not two links, this is just that from B to E there is a one link and from E to B there is another link, okay. So, that is what is a directed graph in this particular case. In a directed graph, you may move only in the direction of the edge, you cannot go to the other side. Directed graph can represent a symmetrical relationship. So, it is not a symmetric relationship. Had it been symmetric, then we use undirectional kind of a situation. Some of the relationship which can be represented are roads, networks, right. hyperlink structure of web pages, they all can be represented with the help of this directed graph. Okay. And then we call a subgraph. A subgraph of a graph G is a graph G dash such that V of G dash is a proper subset of V of G, and in fact, it is a subset of V of G, and E G dash is a subset of E of the edges set of G. So, that is how it is going to be. So, it is a graph whose vertices and edges are subsets of another graph. So, if I have a graph A, B, C, D, E, then this particular portion, if I pick up, which is being represented over here, so B, D, S, C. So, this becomes a subgraph of suppose this is G and this becomes G dash. So, this is a subgraph of this particular graph. All right. So, that is the definition, and then comes the finally the definition of connected graph. So, an undirected graph is said to be connected. So, undirected graph we have used, we have defined this particular term in case of undirected graph is said to be connected if for every pair of two different vertices Vi, Vj, there is a path between these two vertices. So, there is a path from B to D, there is a path from C to D, there is a path from B to C. So, for every pair of vertices, there is a path existing. So, this is a connected graph in this particular case. Now, let us look into some of the graph representation scripts. All right. What do we mean by graph representation? As we saw that we represented graph pictorially, right? Now, that pictorial representation is to be converted into a representation that can be understood by the computer, and that is what is going to be the graph representation scheme. That is, graph representation converts graph to a format that is that computer platform can use. So, we got to use it in a format which can be computationally accessible, all right, and not pictorially accessible. So, for writing efficient algorithms, the logical representation of the graph is very critical if you want to do better algorithmic writing. You should be aware about the way graph is being represented computationally. There are two common computational representation of graph. Okay, one of them is called adjacency matrix, another is called adjacency list. And there are other representations also as far as graph representations are concerned, which include something called linked list, contiguous list, and combination of these lists. However, they are used from case to case basis. The selection of a particular representation depend on applications and function one want to perform on those graphs. However, the general thumb rule is if a graph is sparse, that is the number of edges, okay, which is represented by modulo E, that is the size of the vertex, the set of edges. Okay. So, the number of edges is quite less than the number of vertices square. Then we say that adjacent list representation is preferred, and the graph is, this is a sparse graph. That means the number of edges are very less. Okay. Whereas, in the dense graph, the number of edges are very close to, that is V square, and adjacency matrix representation will be preferred in such cases. So, let us look into these representation. The first one is called the adjacency matrix. The adjacency matrix in a graph with V vertices is a V cross V Boolean matrix. So, it is going to be some Boolean matrix with one row and one column each for graphs vertices. Looks very difficult to understand, but now you can make out that what does it mean. Okay. So, there are 6 vertices over here, all right. So, we have 6 vertices. So, we have 6 cross 6, all right. we have a 6 cross 6 matrix representing. Now, this matrix is Boolean. That is the only thing. Okay? So, that is what it means. Adjacency matrix representation is typically used to represent both directed and undirected graphs, where the number of edges in graph is dense in nature, right. So, dense in nature means most of the values in this particular graph are going to be ones, right, except the diagonal values. Why diagonal values? Because we are not allowing self edges. If we allow self edges, then only the diagonal value will be 1. Otherwise, most of the time diagonal values are going to be 0. So, the Boolean matrix, what we have, Aij is 1 if there is an edge between Ai and Aj node, right. Otherwise, Aij is 0. So, let us look into it. We have an edge from A to B, right. So, we have an edge from A to B. So, this is 1, all right. And on the converse side, there is an edge from B to A. So, this is also 1. Since this is typically an undirected graph, that is why you will find it is going to be symmetric. Okay. So, it is easy to determine if an edge between two vertices in a graph or not. So, we can easily determine the information that there are edges or not between two particular pair of vertices, or one pair of vertices. To find how many edges are in the graph, we will require to at least order of v square times, as there are v square entries to be examined except the diagonal elements which are zeros. The adjacency matrix is symmetric for an undirected graph, but may or may not be symmetric for a directed graph. And space complexity is obviously we are representing into v square number of bits. So, that is what is the v square representation is. Now, what I want you to go through this particular diagram very carefully and identify there is an error somewhere in this particular representation. And what you can see, since this is an undirected graph, all right, therefore, it has to be symmetric. So, if the symmetry is broken over here, in fact, this value should be 0. So, if you just do that particular change, you make it 0 and you will find that this particular adjacency matrix is perfectly representing this particular graph. All right. So, you can check it that there are edges from C to A, C to B, C to D and C to F, right. So, if I see C to A, C to B, C to D and C to F. So, like that you can check anywhere and you can find out that obviously this is even in the same column also it is going to be the same. So, it is symmetric. Okay. This particular value is also going to be symmetric, all right. This value with this. So, this is symmetric. Then next value is this, all right. It is also symmetric here, okay. And this value, okay. So, this value with this is symmetric. So, you can see that symmetry is the main hallmark of when we are dealing with adjacency matrix kind of representation of graph. Okay. Next is the adjacency list. Well, they are used in graphs where the number of edges is much less than the square of the, basically that is the possible number of total number of possible edges which are possible in that particular graph. So, the adjacency list is represented as an array of V linked lists. Now, this is going to be slightly more difficult to understand, but try to think in a very simple way, that we will have V number of linked lists. And if I can help you with that. So, what we have, suppose in our example what you can see, how many nodes are there? We have 5 nodes represented as 0, 1, 2, 3 and 4, okay. And these vertices, so this is one linked list, this is second linked list, third, fourth and fifth. So, for every node we are making one linked list. All right. So this is what, that is why the adjacency list is represented as array of V, the number of, the number of equivalent to number of nodes linked list. If there is an undirected graph with V vertices and E edges, adjacency list representation requires V head nodes and 2 times E adjacency list nodes. Now, this is a very interesting statement to make, and the amount of space requirement required is order of V plus E. So, let us look into node 0. Okay. So, for node 0, the adjacent nodes 0 to 4. So, there exists 0 to 1 edge and 0 to 4. So, that from node 0, we have an edge to 1. So, that is basically the first edge 0 to 1, and 0 is also adjacent to node 4. So, what we are representing 0 to 1 is being represented here, and edge 0 to 4 is being represented here. So, there are two links, right? There are two edges from node 0, 0 to 1 and 0 to 4, and this slash indicates that end of the list. All right. So, we have two nodes which are adjacent to it. What about 1? When we are looking into node 1, we have 1, 2 and 3. So, there is from 1 to and 4th obviously to this. So, 1 to 0, that becomes the first one, all right. Then 1 to 4 is another link. Then 1 to 3, okay, or 1 to 2 is another link, all right. And then 1 to 3 is this last link. So, we have like 1 to 0, this represents that node, 1 to 4, it represents this particular the edge, 1 to 2 represents this particular edge, and 1 to 3 basically represents this particular thing, represents that link, represents the last edge, and that shows the termination of linked list. So, these are not uh, to be considered. All right. What about 2? So, from 2 we have 2 to 1 and 2 to 3. So, we have from node 2 we have a link to 1, from node 2 we have a link or edge to node 3. So, we get 2 to 1 and 2 to 3, and that is the end of the list. Similarly, from node 3 we see, from node 3 we have 1, 2 and 3. So, from 3 to 1, then 3 to 4, okay, and 3 to 2. So, this is also not to be considered. Okay. So, 3 to 1, 3 to 4 and 3 to 2. So, this becomes the link of node 3, and for 4, once again you have 3 links, 4 to 3, 4 to 0 and 4 to 1. So, that is how you will be having 3 links available. So, this is the linked representation. So, typical link representation when we are representing a graph. So, we have got two representations for graph. First one is basically what we are saying is the that is the adjacency matrix representation, where we are representing in the V cross V way of representing matrix with the help of Boolean matrix, although, and in the linked list or the linked representation of graph, we have adjacency list, where we are marking, where we have that is the number of lists is equal to the number of nodes, and each edge is being represented in there. Now, notice one particular thing. If I say 0 to 1, or let us take a link from 1 to 3, all right. So, now from 1 to 3 link is represented in this particular list, all right. So, this is representing 1 to 3, this particular link, okay. This is an undirected graph, as well as in 3 to 1, this particular link is being represented. So, this particular edge of the graph is represented how many times in this particular representation? 2 times, because this is an undirected graph, right? So, it is being represented 2 times. So, that is why this, when we said 2 times the number of edges, right? That is what it means, okay? So, 2 times number of edges, because each edge in this adjacency list is being represented twice, because it is undirectional link. Had it been directional, it would have been represented only once. So, that is where you need to make a distinction. All right? Okay. Now, move on to something called graph traversal schemes. Now, graph traversal schemes are primarily meant for to navigate in a given graph among all possible vertices. Okay? So, these algorithms will help to find the nodes and make paths that are shortest path, feasible path, or prioritized path in nature. So, this kind of algorithms, which we say traversal algorithms, are quite useful where we want to search the entire graph. All right. Obviously, when you are searching an entire graph, you will search in a typical way. All right. And that is why graph traversal schemes comes in. So, graph traversals, so given a graph G having a set of vertices V and set of edges E, our objective is to visit all the vertices in G from a given start vertex. Now, that given vertex will be defined by U only. All right. So, there are two main techniques as far as graph traversal are concerned. One is called depth first search and the second one is called breadth first search. So, let us look into depth first search first. It is also called depth first search, DFS. So, DFS starts with any arbitrary vertex in a graph and traverses to the deepest node as far as possible and then backtracks. All right. So, we need to remember, any traversal technique has to visit all the nodes. All right. So, it will go deeper and deeper, deeper and deeper into the graph. All right. And once there is no further depth, then it traverses back. Okay. So, the algorithm proceeds as follows. It starts with selecting any arbitrary vertex as the start vertex. So, select any vertex as start, then traverses to the next unexplored vertex W, which is adjacent to the starting vertex V. Adjacent says that there is an edge to that particular vertex. All right. So, you will go to that particular vertex which is adjacent to the vertex. It continues until no adjacent vertex in the is left to be examined, and if the last vertex is U, okay, which does not have any adjacent vertex, all right, it backtracks to W and explores the unvisited adjacent node. Okay. So, the traversal process terminates when all the vertices are traversed. Now, this is a very simple process. Okay. So, let us look into the DFS algorithm and then we will take into look into one of the example of it. Now, if we say DFS V is a function, okay. So, V we are assuming is the starting vertex of the graph. So, if we start with the starting vertex V of the graph, okay, and the input is basically GVE, that is the graph itself, where all the vertices are informed about the edges. We will be informing that particular thing, and how we will be informing? We will be using one of the representative schemes, okay, like representation schemes. Either we will use adjacency matrix or we will use the adjacency list. One of these two way we will be defining our graph. So, that input to the graph actually is in the form of its representation scheme only. And we are defining another array called visited, where n happens to be the maximum number of node. So, visited basically defines if a particular node has been visited or not, and we will initialize this particular visited nodes or array of visited to 0. Okay. So, that is what we will be going ahead. Okay. So, visited v equals to 1 means okay. So, since we are starting with node v, so we have visited that particular node. So, it will be initialized to 1. So, for each vertex w adjacent to v, do if visited w equals 0. That means the w has not been visited. So, what we are doing? We are starting with v, all right, the vertex small v, okay, the start vertex. And for that start vertex, for each start vertex, what we are doing? We are assuming that w any which is an adjacent to this particular node v, small v, okay, if it has not been visited, if this particular node is not visited, okay, not it has not yet been visited, then we perform that is depth first search starting with w. Okay. So, we do a recursive call and it will keep on happening. So, how this particular thing proceeds, let us try to do with the help of an example. So, this is my graph, all right, and I want to do the depth first search traversal, and the start node is, let us say, node 1. So, how I am going to do? So, my first call is going to be DFS 1. So, as soon as when my start node is I will be calling with DFS 1, all right, and I will be making visited the first location as 1. That means, this particular node 1 has been visited, all right. Now, this particular thing, what is next? Now, from here, okay, since now we pick up the adjacent vertex of this. So, that w, okay. So, this becomes the w vertex, all right. Now, what we find, so we have got to do for each and every w of it. So, this is one, this is another, and this is third. So, there are 3 adjacent nodes for it. So, this may be let us call it small 1, small 2 and Roman 3 numbering. So, we start with Roman 1, okay. So, this becomes w. So, we pick up 2, all right. So, now we pick up 2 and visited 2 is assigned 1. So, because 2 has been visited, all right. So, next, okay, now there are 2 adjacents to it, all right. So, we pick 3, okay. So, now w becomes 3. So, we visit 3 and visited 3 becomes 1, all right. Like that, we will keep on changing the value of visited array. Now, similarly, 3 will call now 4, w as 4 now. So, now we will visit 4, all right. So, 4 will be visited and visited will be made 1, then it will be calling 5. So, now the next in the depth first search will be 5 will be visited, okay. So, once 5 has been visited, what we find that this node as well as 4, both have been visited already, all right, because the value of visited 4 as well as visited 2, both are 1. So, both these nodes have been visited, we backtrack. Okay. Now, what are the adjacent to 4? 3 only, there is no more after 5, there is no more adjacent. So, it comes back to 3. So, we backtrack to 3. Now, 3 also does not have any other node which is to be visited, backtrack to 2, then backtrack to 1. So, at 1 we find that 6 has not been visited. That is why we visit 6 after 1, all right. So, we visit 6, then from 6 once again it is a depth first search. So, we will go to 7. Okay. So, from 6 we will visit 7, from 7 we will visit 8, and at 8 we come to know that all the nodes have been visited. So, we can actually you can backtrack and come back at any point of time, but ultimately this algorithm is going to terminate And what you have done, the result of this particular algorithm is that you have visited all the vertices in a depth first search fashion. Okay. Now, what is the complexity of this depth first search algorithm? So, suppose G with vertex set V and capital E is set of edges is an undirected graph, right, with modulo V is number of nodes and E being number of edges and represented through the adjacency list. So, if we are using adjacency list, then a sum of lengths of the adjacency list is 2 to the power 2E, right, that we have already computed. DFS reads each node only once in the adjacency list. So, okay, so each node we will be visiting, and each node in the adjacency list we will be visiting. And what is the size of this particular adjacency list was? Order V, because there were V head nodes, and E basically is because of number of edges, although the 2 is there, but in order it can simply be ignored. So, the order of this particular computation is order V plus E. If the graph is represented through its adjacency matrix, the time to determine all adjacent matrix to the starting node V is of order V only. Alright. So, that is number of nodes. Since at most V vertices are to be visited, the total running time will become V into V. So, it is basically order of V square, which is basically size of the matrix as for which you have created in the representation. Now, let us look into another algorithm, which is breadth first search, which is called BFS also. Now, BFS starts from any arbitrary starting vertex and visits all its adjacent vertex at the first level. It then moves to the second level to visit all the unvisited vertices adjacent to vertices at the first level, and then so on and on and on, right. So, this is how we will be doing first level, second level, third level and onwards. So, Q is the main data structure that is used to implement this particular algorithm, and this particular algorithm, in fact, the same logic is used in Dijkstra's single source shortest path algorithm and Prim's minimum cost spanning tree problem, which we will be discussing later on. So, what is this BFS algorithm? So, BFS algorithm is basically goes with this. It takes one parameter V, which is the starting vertex of the graph. So, let Q be the Q data structure which is to be used. So, what we will be doing? We will be inserting this particular the starting vertex into the Q, okay, until all its neighbor vertices are finished. So, we will be inserting just V right now. So, and then we say we will mark V as 1 because it has been visited, okay, otherwise 0, and we will print the Q at this point of time, which basically just consists of the vertex V. While Q is not empty, now Q is not empty because it contains V, right. So, that is the starting point. So, we move that particular element, we remove first element to a node called small v, okay, and then process all its neighbor. So, for all neighbors W of this particular node, okay, in a graph G, if W is not visited, insert that particular node into the Q, all right, and okay, and then you have visited this W. So, you have visited it, mark it visited and print it into the queue. All right. So, this is how this particular algorithm works, and if we can explain it with the help of an example, then it will be better. So, let us look into the example. So, how does it work? Once again the same graph, but now what we are doing? BFS, and the start node once again is 1, node 1. So, we are starting from node 1. Okay. So, now this is my node 1, this is in the queue and this has been, it has been visited, right. So, visited for this is basically 1. So, visited this node has been visited. Now what happens? What are the adjacent node for this? 2, 6 and 8, right? So 2 will be put in the queue, 6 will be put into the queue, 8 will be put into the queue. And during when we are putting these values, we are marking them as visited, as well as we are putting them into the queue. So what we will be getting? 1 and then 2, 6 and 8. All right. So at the next level, so 2, 6 and 8 has been visited. All right. Now at the next level, we will be visiting all the adjacent vertex of 2. So the adjacent vertex to 2 are 3 and 5, right? So we will be visiting 3 and 5, all right. Then we will be, after we visited 3 and 5, okay, we will put them into the queue. So now the queue will contain 2, 2, 6, 8, 3, 5, 2 has already been removed, all right. So now this is my queue, okay. So now I remove 6 from the queue. And what is the adjacent? Okay, so 7, okay, this is basically marked visited, all right. Next, 8, 8 has no other further adjacent, so nothing is to be done. 3, once again it will be removed, 5 will be removed, 7 will be removed because all has been moved, except when we do the 3 one, 4 will be inserted over there, right. So 4, because for 3 and 5, 4 is there. So then at the next level, what you see after 260 is 268, 2, 6 and 8 respectively, what are the next nodes? 2 adjacent to 2 are 3 and 5, which we inserted, and adjacent to 6 and 8 is 7. So that is what also we inserted. All right. And finally, it will be 4, which is the at the third level, we will be inserting 4 into the queue, and then we will be marking it as visited, and thereafter we will be getting this in our print order, that is 1, 2, 6, 8, 3, 5, 7 and 4. Okay, this is the same order 2, 6, 8, 3, 5, 7 and 4. This is the way we will be inserting it into the queue, and we will be checking also whether this particular node has any adjacent vertices of this particular node has been left unvisited or not, right. And this is the important parameter which you are using, or important variable which you are using, is the visited variable, which basically defines whether the node has already been visited or has already been traversed with the help of this particular algorithm. So now you can appreciate the difference. Okay, when we are doing the breadth first search, our search is for 1, 2, 6, node 6, node 8, node 3, 5, 7, 4. Whereas if you remember, our depth first search was for 1, 2, 3, 4, 5, 6, 7, 8. That is how our depth first search was. So both the orders are different, however, the objective has been achieved, and in both the cases the entire that is graph has been traversed. So what is the time complexity? Once again, the time complexity is of the order V plus E, where order V is the total time to complete the queue operations, all right, including insertion and deletion of vertices in the queue. Okay, insertion and deletion of single vertex takes order 1 time, and since there are V vertices in the graph, it will take order V time only. Okay. So the time taken to traverse each adjacency list only once is order of E. Therefore, the overall time is order V plus E. Right. So this is same order as we had the for the depth first search. So time complexity of both the depth first search and breadth first search happens to be the same. So let us summarize what we have covered in today's session. We have defined the graph and its representation. And representation, basically we mean that representation in computer. Those two schemes which were defined were adjacency matrix and adjacency list. Okay. Then we also defined the different types of graph very briefly though. and we discussed about two main algorithms of graph traversal, which are depth first search and breadth first search, and we defined the complexity of these two algorithms. With this, we end this particular session. Bye for now.